some basic questions about nuclear power in Japan. What is the status of nuclear power in Japan?
You mean nuclear fission reactor plant?
Yes, the conventional nuclear power.
You know, currently we have only nuclear power plants in operation. We have altogether 54 nuclear power plants all over Japan. So another 52 are all shut down. And however, 4 reactors are broken by earthquake and tsunami event in Fukushima. And so far the government is wondering whether we need to start up again another rest nuclear power plant, making a rest now.
Right.
So we need a new regulatory system, and this is a governmental organization, Nuclear Regulatory Commission, is now testing the application from many electronic companies. So that will take another 3-4 months.
But right
make
now,
approval.
all nuclear power is shut down.
Only 2 reactors are in operation. Only 2 in Kansai Electric Power.
Now, what is the level of support for your research, for cold fusion, LENR research in Japan?
In Japan is very poor now. Very luckily, we have been supported by private company. However, only a little bit money, of course, not much. And I'm belonging to Technova Incorporation, headquartered in Tokyo. However, we are working in Kobe, in West Japan, near Osaka, doing experiments kind with Professor Kitamura. We are all retired professors from university, so we have no fund, no laboratory regularly, so we have to rent some place. Now we have a place in Kobe University. Professor Kitamura used to have a place here, so we are continuing to use that system. Getting a little bit fund from Technova company, feeding to university. In that way, we can survive there and do this kind of experiment. That's a least effort, no governmental support.
So, would you say there is a strong academic and industry collaboration?
Not very strong. Not very strong. We have collaboration with industry people supporting our work and providing a little bit fund. However, they are interested in the final result. If the results are very fantastic, to apply for industrial say products, energy producing devices and so on. And they are just watching, and we are doing experiment, research, and providing this kind of results. And they are day by day getting more and more interested in now, but still do not decide to feed a lot of money yet. That's the status now.
Industry is interested in a commercial product. Academics are interested in research. How do those two things come together in collaboration? How do you work that out?
So that, of course, our academicians are interested in say, physics mechanism and so on. What's going on there? What's the secret of this kind of phenomenon? Excess heat and nuclear. What's secret? That's our interest. Of course, industry people want to have profit from that, of course. So we need to compromise somehow. Okay, we provide this kind of basic data and say maybe in extension we might have energy producing, device in this way. If we have, for example, this 4 watt excess was produced by only 2 gram nickel. If we put in 100 or 200 gram of nickel, we have 100 times 400 watt. Okay, so that makes enough power for providing energy for every day for one house, one family, something. So we can make a small distributed type energy source in future. Very compact and unfortunately, this kind of phenomenon doesn't produce any radiation until now. So it looks like nuclear, but no radiation, no harm nuclear products. So we can make a small device with big power and distributable. And,
so you are making, you are making kilowatt power.
For example, if we scale up the system to put in just with 2 gram nickel, if we use 2 kilogram nickel, we have 4 kilowatt. That's already commercial base energy producing device. Of course, to do that we need research and development, technology development with many people. We need to accumulate technical know-how.
So you pretty much have a device that you are ready to scale up?
Yeah. We have done the first trial with scale-up system from this one 10 times, and we'll show the result on Thursday morning by Dr. Kitamura. We show very nice effect. So by using that device, just putting the 10 times the nickel powder, we would see maybe kilowatt with that apparatus. Then we can say proudly, okay, come on, industrial people, we can now apply this device to something like that. That would come in a year or in 2 years, we hope.
This is nuclear power.
Probably.
This is nuclear, but it doesn't produce radiation. Can you describe how clean this is?
This experiment shows about 800 electrons per nickel atom. That's too big by chemical. Chemistry can produce only 1 electron per nickel, something at most. So 800 times. That is too much. Probably no other explanation than nuclear. However, what kind of nuclear, we don't know. I have a working nuclear model. That's a 4D, 4 hydrogen, 4 deuterium cluster making a collapse. So I have a tetrahedral symmetric condensed model. I have a theoretical presentation on Thursday also.
What is the name of your model?
TSC model, tetrahedral symmetric condensate. Very complicated, of course. This is academic names.
What is your favorite word to use to describe this? There are many names for this reaction.
Yes.
Cold fusion, Lanner, quantum. What do you like to call it?
This is a kind of cold fusion, but cluster fusion. Cluster type cold fusion, not binary reaction, not 2. 4, 6, 8, 12. That kind of combination is possible by theory. We have a series of theoretical explanations.
Why is this technology important for the world?
Because that produces clean, high intensity energy. Only using small amount of material. So we have a big energy coming out and no harmful radiation coming out. And also by using very cheap material like nickel and hydrogen, very cheap. So very important. That can be a great amount of energy source for future human beings. We hope.
Well, yeah, at that point though, it was kind of up in the air.
That's a great hope.
Thank you so much.